Now, it's time to relate thermodynamics to equilibrium and the equilibrium constant. The thermodynamics is the study of reactions that essentially have large changes in heat energy and the related changes in entropy. And so there tend to be easiest to measure delta H, delta S, and delta G values. And so they tend to be combustion reactions or reactions like that, big changes in heat. Now, equilibrium constants tend to be reactions in which you can measure the concentrations in solution or the partial pressures of gases. And both of them tell you about, is a reaction spontaneous in the forward direction, and what is the position of equilibrium. So now it's time to relate them. And what we're going to do is we're going to come back to Q, which is the reaction quotient, and QC. We'll start with QC, although everything I'm saying here is true for QC and is also true for QP. QC for the general reaction is products raised to coefficients over reactants concentrations raised to coefficients. And now what we're going to do is we're going to compare let's talk. So this is the reaction quotient. And it is the reaction quotient. It's the same expression as Kc, except that Kc is required to be at equilibrium. QC is not. QC is just any set of conditions we decide to put in here. And the relationship between QC and Kc tells us whether a reaction needs to go in the forward direction, whether it needs to go in the reverse direction, or whether it's at equilibrium. So reaction quotient, so any concentrations, and Kc would be equilibrium concentrations. So now what we're going to do is I'm going to create a little table here. It's going to be condition. It's going to be delta G not reaction. And it's going to be QC, QC, I guess, in this case. And actually it's going to, so yes. So let's suppose that the reaction is at equilibrium. And what we've said is that delta G, when a reaction is at equilibrium, equals 0. And QC equals Kc. And now, if a reaction is spontaneous in the forward direction, we know that delta G is negative, so delta G is less than 0. And we know that QC, to have the reaction be going in the forward direction, forward, one of those directions, has to be less than Kc. And now, non-spontaneous in the forward direction. Which is also equal to spontaneous in the reverse direction. Well, non-spontaneous in the forward direction is mostly what we've talked about now, but it turns out that it's equivalent to being spontaneous in the reverse direction is when delta G is positive. And QC is greater than Kc is what we mentioned when we talked about equilibrium. That means do the reverse reaction. And now we're saying it means spontaneous in the reverse direction. Those are the same things. Now let's come up with a third column, QC over KC, and then we're going to actually take the natural logarithm of that. So when QC over equals KC, QC over KC is 1, and the natural logarithm of 1 equals 0. Is that right? Yes. Okay, good. Then spontaneous in the forward direction, so that means this number is bigger. That means ln of QC over KC is going to, QC is smaller, which means that the natural logarithm of these is going to be less than 0. And if QC is bigger than KC, the natural logarithm is greater than 0. And this is not a proof by any means of what I'm about to do, but it does show you that there's a correspondence, at least in sign, between delta G not reaction and ln of QC over KC. They all have the same trends. That's as much as we're going to do, and then I'm going to introduce the direct relationship between delta G reaction and ln of Q over K. And it goes like this. Delta G now without the not reaction equals RT ln Q over K, where Q could be a QC and K a KC, QP, KP. It all depends on the reaction, as we'll see. So, and what this means is that the conditions of pressure and concentration are no longer standard. So concentrations, that's square brackets, and partial pressures, we'll put concentration of A, whatever that is, and partial pressures are no longer standard. That's why the not is gone. And we didn't take it away before because we didn't want too many delta G's running around. Okay. Now, we can break this down further because any two numbers that are divided inside the natural logarithm are subtracted outside. So delta G reaction equals RT ln Q minus RT ln K. And so again, then this is a very general equation, but let's do some more work with it. So in the unusual case, so now we're going to go back to standard conditions. At standard conditions, concentrations of A or anything equals 1 molar, and partial pressures of all species equals 1 atm, so Q equals 1. And natural logarithm of 1 equals 0, so at standard conditions, Q equals 1, ln Q equals 0. And when we put the not back in, we see that the change in free energy of reaction under standard conditions equals minus RT ln K, where K is the equilibrium constant and delta G is the free energy of reaction. And so this is an equation that we will use quite a bit. This is an equation that we can use, and then we'll create a third equation that will be the most powerful equation in this chapter, where instead of RT minus RT ln K here, we will put in delta G not reaction. So delta G reaction with no not, I know, sort of a double negative, but bear with me, equals RT ln Q plus delta G naught reaction. And the reason this is so powerful is we can now calculate the free energy under any conditions because we can now calculate delta G at any temp using delta G naught reaction equals delta H minus T delta S. Right here. And here we have calculate the contribution to the free energy based on different molarities and pressures. So contribution due to non-standard concentrations and pressures. And that's everything. That's everything we can change. Now we can figure out delta G. We can figure out whether a reaction is spontaneous under any set of conditions we're given. And it is true that you can think of delta G naught reaction as the big term here, meaning that this is the course adjust. You choose this part, and then if you want to change the fine details of delta G, you can change the operating conditions. Let's show you a little bit more about what I mean. Oops, did I do 2 pages in 1 page again? Yes, so done on previous page. Sorry if you ran out of space there. Let me just double check. Yep, done on the previous page. Now let's get to the example. No wonder I felt like we were ready for the example. It says, is the following reaction spontaneous at T equals 25 degrees Celsius and partial pressure of carbon dioxide equals 121 atmospheres? What is K? Let me write the reaction. Goes to calcium oxide. Calcium carbonate, solid, goes to calcium oxide plus carbon dioxide. We'll write out delta HF, S naught, delta G, and all of our units. And then we'll run through the whole process because we've got everything we need right now. Delta HF, oh, we're at 25 degrees Celsius. We'll do another temperature in a minute. Says, and these are all on our conversion and equation sheets. So if you look for those, right at the top is calcium carbonate solid, minus 1207.6. 91.7, minus 1129.1. Calcium oxide, minus 634.9. 38.1, minus 603.3, minus 393.5. Carbon dioxide, one of the more popular things to have in reactions. All right, so now we got all our values. And we're asked, is the following reaction spontaneous at 25 degrees Celsius, standard, and partial pressure of carbon dioxide, 121. So let's multiply these out. It's going to be products minus reactants to get each of these values. minus 634.9 minus 393.5, 393.5 minus 1028 minus the reactants, which are negative, so plus 1207.6, positive 179.2, very endothermic, tends to not be spontaneous. We have a gas over here, so I bet you the entropy is going to increase. We can see that from the numbers. 213.8 plus 38.1 minus 91.7. We get 160.2. Those are joules per mole Kelvin. And this tends to be spontaneous. So, right, tends to spawn there. And since we're at 25, let's calculate delta G reaction. We get minus 603.3 minus 394.4 plus 1129.1. We get 131.4 kilojoules per mole. Non-spawn, under standard conditions, which includes 25 degrees at standard conditions. But we're not at standard conditions, even at 25 degrees Celsius, because we have a partial pressure. So now let's go back. Let's look at our possibilities here. So it looks like we have delta G naught reaction. We have a second set of conditions here, of which the only thing that's not a solid is the gas. So we'll calculate a QP this time, since we have a partial pressure. Oh, and we're asked what K is too. Well, we got a little bit of work to do. So let's do the K part first. We have this right here, and I will now solve for K. So, and then we'll do the next part. Delta G reaction equals minus RT ln K. Now let's, well, however you do this, let's get the RT to the other side and the minus sign. We get ln K equals delta G minus reaction over RT. We take the exponential of both sides, and we end up with K equals E to the minus delta G naught reaction over RT. No wonder I have a second page here. Let's just do this one on this page. And then we will do the next one on the next page. Yes. And I guess that's all we'll do. Well, let's see. E to the minus, well, this is in kilojoules. R is going to be in joules, so minus 131,400 joules per mole, divided by R, which is 8.314. Joules per mole Kelvin times 298. So 131,400 minus divided by 8.314 divided by 298 minus 53. Now let's take the exponential of that. 9.27 times 10 to the minus 24. Okay, under standard conditions with a K value like that, we would say this reaction goes nowhere. Or equilibrium favors reactants. That's what we would say in the equilibrium chapter. Now in the thermodynamic chapter, we would say this reaction is non-spontaneous and it would take a large amount of energy to make it happen. We could. And we could also say there is a temperature above which this reaction becomes spontaneous. I don't know what it is. Actually, let's solve for this condition first. So what is K? We did that first. Now let's do this condition, and then we'll see if we have any space left to find the temperature. All right, so we come back to this reaction. We have a contribution due to non-standard pressure. Let's calculate, let's write this reaction first. So this equation. Delta G reaction equals, will we be able, there we go. RT-ln-Q plus delta G naught reaction. All right, so now we know that delta G naught reaction is 131.4, and this R still in joules, so I'm going to write 131,400 joules per mole. I'll give myself a little more space. My RT, ln, and now my Q. Q is products over reactants, so this is a product. My Q is just partial pressure of CO2. And so I'm going to plug in 121 atmospheres here. Does have to be in atmospheres, actually. And add my 131. So let's see what we get. So this term, 121, natural logarithm times R times T, 11,881. This is in joules per mole Kelvin for my R. T is in Kelvin, so I get joules per mole plus 131,400. And I guess technically I should round that to a 2 and add it to my 131,400. And I'm going to get, well, let's just do it exactly. 143,282 joules per mole, or 143.3 kilojoules per mole. Still non-spontaneous. And in fact, more so. It takes more free energy because you're at a higher pressure. And instead of solving for the temperature, we've done that already. Now we've shown you how to use this equation. We've shown you how to solve for the equilibrium constant when you have a delta G value. And those are the things we wanted to do here. And those are all the things I wanted to do in this video.